I'm Charles, and I'm on a mission to find what's inside everything. To help me get my answers, I have an industrial CT scanner. It takes a whole bunch of X-ray images from all around a subject, then builds a 3D model revealing every internal detail. Today, we're scanning a PS5 controller and an Xbox One controller. We'll scan them each for a few hours and see how they stack up. No matter where you like resting your left thumb while playing your games, I think we can all agree making a good game controller is pretty much a solved problem at this point. These two both do the exact same thing, look almost the exact same, and break almost the exact same. But if I go out and buy them right now, the Xbox controller is $70, while the PlayStation 5 controller is $95. What's making the PlayStation version cost 35% more, and why do they still both develop stick drift at that price point? Let's take a look at our scans. I grew up on PlayStation, not Xbox, so I like the symmetric controller, but reasonable minds can disagree. Oh, that is crisp. There's a lot going on in here, man. We're trying to figure out why the PlayStation controller costs $25 more than the Xbox controller. And the first reason is that the PlayStation controller has a lithium polymer battery in it, and the Xbox controller has some user-supplied alkaline batteries in it. We didn't need a 3D scanner to figure this one out. They're there. I personally think the PS5 controller, that's a better design to have a rechargeable battery. Our first reason that it's more expensive then is battery. What else do we have to blame? Ooh, okay, this is a cool design feature on the Xbox One here. This is the D-pad. And on Xbox, it's a pretty nice part. Like, that feels good. On the PS5, there's buttons there, but they feel a bit more mushy, I feel. There seems to be something pretty funky going on with the D-pad on both these controllers. So I'm gonna bake in an ROI on both of them, and then we can zoom in a little tighter. You can see in this cross-section the single injection molded piece of plastic that forms all the buttons of the D-pad on here. These all rock together, and that's because that's a single piece of plastic forming 4 buttons. The Xbox does the same thing. It's just a little more obvious because the whole thing's exposed. So when we peel back the plastic here, what we can see, first and foremost, is a spring. Like a big spring. This is going to be a piece of stamped sheet spring steel, and it's what's actually keeping this preloaded up and resisting motion and giving it that nice, satisfying click. Now, what in here is actually doing the clicking? I'm not too sure, because there aren't tactile switches on the circuit board. Instead, we just see these round contact patches. So that means that on the underside of this piece of plastic, there's going to be a carbon patch coated onto the plastic somehow, over top of some silicone or something with some deflection. And that's going to bridge the contacts on the circuit board from here to the surrounding ring when you push down on that corner. So you mush this down, and it's going to bridge this contact to this contact. And that's how you detect which direction you're pressing the D-pad. This ring would be a fairly expensive part in the grand scheme of things, compared to injection molded plastic. So I'm curious to see whether Sony did it the same way. Now that I've gone and adjusted things, we can actually see how Sony is getting their kind of mushy action on this, as opposed to Microsoft's hard piece of spring steel. This is kind of cool. So right here, you can see the edge of a dome. That's going to be a conical shape, and I suspect that's going to be made out of silicon or rubber of some sort. The reason it feels a little mushier is because you're compressing that silicon, probably, dome into itself, and that's going to feel a lot squishier than the nice, snappy click, 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 click that comes from a piece of spring steel. Of the two of them, I think this sounds better. As a general rule, I'd expect to find some metal somewhere to actually conduct the electrical signal from this switch or make a contact, but I'm not seeing anything on here. It's like the whole thing is somehow made of plastic. So on the Xbox controller, we can clearly see our contacts here. Up, down, left, and right. When those contacts are bridged by the conductive pad on the underside of the actual, face button, it's going to create an electrical signal. Those are going to trace somewhere along this circuit board, and they need to make it all the way over to the next board down in the sandwich, because that is where this microprocessor lives. So that microcontroller is actually living on its own little daughter board, and it's soldered down to the main board at these little castellated edges here. So this is itself a much bigger circuit board, and all of that together is soldered to a connector somewhere that's going to connect it to the other circuit board. Found it. So right here is a mezzanine connector, and it's called a mezzanine connector because you have a circuit board and then you have another one that's forming, a second story above it. 14 pins on this connector here, and so those two boards just snap together and that sends all those signals between the two sides. Now, 14 pins shouldn't actually be enough for all the stuff that I think is happening on that daughter board. On the Xbox controller, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and probably 13 buttons on that top mezzanine. And we also have our USB port. I think we're going to be running out of pins very quickly. Oh, found it. So there is actually another microcontroller or some other chip. It's tackling some role from actually being on that mezzanine board. I'm happy. Let's see if we can figure out what PlayStation is doing. Guys over at Xbox, as we were just discussing, have 2 circuit boards in here. PlayStation appears to only have the one, and that circuit board doesn't go up to where the face buttons are. So is there something else in there that's making those contacts? If they had a lightweight, flexible circuit board, that probably wouldn't show up on here at all. So far, the PS5's up 1 battery, but it's down 1 on the D-pad. So where are they making up the rest of that value? I'm pretty sure one little piece of stamped spring steel, that's not $35. I suspect that isn't even 10 cents in the finished product. In the case of the Xbox controller, we can make out pretty easily that we have 4 vibration motors. And those are going to have some amount of cost associated with them. In the PS5, we can still make out pretty clearly that there is a motor, a motor, a motor, and a motor. But they're not all doing vibration. Aha! Because this isn't a motor in the traditional sense. It doesn't spin. Now what it does is it has a mass inside of here attached to a spring on this end and a spring on this end. And it's shaking it linearly. That can be done with like a really high degree of precision to actually form a linear resonant actuator. But these are a little fancier and probably a bit more expensive unless you're making several million of them, which they are. It's because instead of having, your tiny little brushed DC motor in here spinning a weight that's off center and causing a shake, you're actually able to precisely control what amplitude and frequency of shaking you're getting. I'd expect it to be a better user experience, which I presume Sony did too, otherwise they probably wouldn't have done it. These other 2 motors, they aren't just shaking things, no. These, through some arcane magic that I don't fully understand, these actually adjust the stiffness of the triggers programmatically. We have our motor, and we have our worm gear. You can pretty clearly make out the gearing here. That's impinging on this bull gear, and that bull gear actually is a gear reduction, because it has this pinion attached to the same shaft. It's the same piece of plastic. It's literally the same element. And that is riding against this little arc of a spur gear. That small section of an internal gear actually runs forward and grows out a bit here into an element that goes around to the same pivot pin as the main trigger. This trigger only has, 30 degrees of motion, and that needs to translate into quite a bit more on that spur gear so that this cheap brushed motor can actually keep up with things. So what all this means is that as this trigger moves in, the resistance that it encounters can be adjusted by the turning of this motor, and that motor will actually be back-driven as you run the trigger in. Somewhere in here, I'm expecting to find a spring that actually couples these 2 pieces together, because that would mean that you can adjust the preload and the apparent stiffness of the trigger. So our bigger bull gear winds up spring-loaded this way by this torsion spring right here. Somewhere in Japan, there is a tool and die maker who is involved in manufacturing these parts, and he should be very proud that he got this to work. Because there's a lot going on in here, and I cannot decipher it. That's where the money's going. These triggers are wildly complicated. All the motor is doing in the trigger of the Xbox controller is just giving it a good shake. Xbox is doing one thing that I really like with this design, and that is that instead of using a potentiometer, they're actually using a Hall effect sensor. It's a disc magnet. This one's going to be axially polarized instead of diametrically polarized. On our circuit board, right here above it, a little 3-pin package. And that's just going to be an analog Hall effect sensor. So what that does is it outputs a voltage proportional to the strength of the magnetic field that it's residing in. In this case, as this magnet gets pulled up by pulling the trigger, the magnetic field that's being seen at this chip is going to increase significantly. And that gets you a nice, reliable sensor for the travel of these. I really like what Xbox has done with those triggers and with these face buttons for the D-pad. The intricacy going on inside of here for these triggers, which, just as is, feel a lot nicer without any electromechanical wizardry going on the inside, is really, really impressive on the part of Sony.
I'm not sure who authorized this or who thought it was a good idea, but man, it's impressive to look at. You got 2 extra circuit boards, like 5 more injection molded pieces. That totally justifies the 35% price difference. And on top of that, you also have, of course, a battery, a rechargeable battery that you're not throwing out alkaline cells from playing Fortnite. That's why the PlayStation 5 controller costs more than the Xbox controller. But why do both Xbox controllers and PS5 controllers get stick drift? I'm expecting this to look essentially the exact same between the 2 controllers. In fact, we might be able to find that these parts are manufactured by the same company. Now, of course, a game controller stick can do 3 things. It can go, up, down, left, right, and in. A little click. The position that you're holding the stick in gets sent down into the stem, and that stem goes into a little metal cage here. And that metal cage is what actually contains the transducer. We have a potentiometer here, and that's going to be our x-axis. Potentiometer here, that's going to be our y-axis. As we're scrubbing through here, we have this hard metal ring. That's our rotor. And it's making contact with the stator in these 3 highlighted points. This ring is a thin conductive coating directly onto our rotor. And that's making contact with the wiper. The wiper also has these contacts here, and they are riding on this strip of resistive material around the outside edge. As you rotate the rotor, this contact patch at the top is going to move towards the positive side and towards the negative side. And so if it's in the middle, you'll get half your voltage. If it's all the way to the right, you'll get 0 volts. All the way to the left, you'll get your full voltage. If we look carefully here, you'll notice that there is actually a little different from how I've drawn it. Just this small little region where there's a carbon contact rather than a copper contact. So this range here is actually the entire sensing range for the joystick. You don't actually get that much motion out of a joystick potentiometer. So this tiny little region is actually doing all of the work in terms of resisting wear, and that is where we're going to see some stick drift problems. Because as we're swiping the wiper back and forth and back and forth and back and forth, 10,000 times, cumulatively, is actually going to wear out that resistance. And it's going to change the distribution of resistance throughout that. What's to be done about this? Well, let's see if PlayStation did it any differently. Right off the bat, this is looking suspiciously similar. They're indistinguishable. These are the exact same parts. So any sort of wear problem that you have on the PlayStation, you're gonna have the exact same wear problem on the Xbox, best I can tell. So is there any way to design one of these that doesn't get stick drift? Yes. You can use Hall effect rotary encoders instead of potentiometers to detect the angle of the stick. And those will not exhibit wear problems, but they are a little more expensive. I don't know why they use this exact design, but that is why the sticks drift. And that's kind of cool. So hopefully with all that, you can see why the PlayStation 1 is definitely a more expensive design, and we can also see why the sticks still drift after all these years of research and development. If you enjoyed this video, make sure to leave us a like. And if you want to see inside of something, leave a comment with your suggestion. If you want to support the channel, share this video with a friend, or check out hacksmith.store. And if you want to see inside of everything, get subscribed.